this video, we're going to look at exponential modeling, and we're going to particularly focus on how to graph exponential functions. An exponential function is a function that grows or decays at the same relative amount each time. This is different than linear functions. Linear functions grow or decay at the same absolute amount per time. So linears go up and down by the same amount each time, like plus 10, minus 10, where exponential functions are going to go up or down by a percent. So they increase at 10% or decrease at 12% every time. The Q with the little subscript 0, as we read as Q naught, that's your initial value. So that's how much money you put in the bank when you first started, how many bacteria are in the dish, how many people you have when you first started counting. R is going to be your rate of growth or decay as a decimal, and you're going to add that to a 1. Now, if it's a decay, your R is going to be negative. If it's a growth, your R is going to be positive. T is time. It's usually in years, but it could be in any type of measurement. And then Q without the subscript is the value you'll have after that time is finished. Negative values for R mean that you have a decay. Even though it probably won't say a negative, it will say something like decays or decreases at a rate of, I don't know, 10% or 14%. The time has to be the same for R and T. So I can't say it's decaying at 10% a day, and then I want you to find something per year. I would need to talk about all days or all time. Here's an example. The census in 2010 found the U.S. population to be 309 million. So million, it's going to have 6 zeros after it. The estimated growth rate is 0.9% a year. We want to write an equation for the U.S. population that assumes an exponential growth. If something's growing by a percent, that means you're talking about an exponential. We're going to use that equation to predict what the population would be in 2100. So we'll identify all the important parts. In 2010, I have 309 million. Now you can leave this as 309 and just put million at the end, or you could put all the zeros. Either way is fine. The growth is 0.9%, but when I plug that into my equation, I need to talk about that as a decimal. So I take that 0.9 and I put it right up here. So that's going to be 0.9 over 100, and when I do my division, I get 0.009. It's a growth, right? It's positive. So when I add this on, I'm going to have my initial value of 309 million times, and then in the parentheses, it's always 1 plus whatever your R value is, and if your R is positive, then it's going to stay positive. You're going to add this on, and then I leave the little t on the outside. So T and this Q on the outside are going to stay. 1 plus 009 is just 1.009. And so here's my equation. So if I want to find out what's going on in 2100, that's 90 years later. All I need to do is plug in 90 for T. So I have 309 million times the 1009 raised to the 90th power, and I'm going to get about 692 million. And I'll show you how to put this into your calculator in just a second. If I want to graph this equation right here, where I would leave a t in, I have a couple of different options. I could just plug this into my calculator and have that give me a graph. I'm going to pull up the calculator so that you can see that. I've backed out of the slideshow so I can show you how to use your calculator. If we want to graph our equation that we found in the last slide, 309 million times 1.009 raised to the t, I will pull up my graphing calculator, and yours might look a little bit different, but the process will be the same. You'll turn on your calculator and go into y equals. In here we'll type 309. You can put the times or not. In parentheses 1.009, close that, and then I'm going to raise that to my power, which when I hit my variable key, it will default to an x. X and t are the same thing. That's fine. Then what's going to happen is you're going to hit graph, and you're probably not going to see a whole lot because our numbers are pretty big. So what we'll need to do after this is done thinking about what it should look like is hit zoom. And I usually start with zoom fit. So I'm going to go down to zoom fit and hit enter. And I may or may not see something nice after it figures out. And it doesn't look that great. That's one of the downfalls of using a calculator. It kind of looks like a line, even though it's not. I could zoom out a little bit. If I put this right on the middle, it might look a little bit better. If you still want to use technology, really a better choice might be to use Desmos. Desmos is an online graphing calculator that will be helpful with your lab for this section. And you can type in 309 times 1.009, and to get it to be in an exponent, use the caret key, which is Shift 6, and then you put in your X, and then I'm going to push this out a little bit and hit equals, and I'll put a Y in here. And when I hit enter, again, it doesn't look like you can see a whole lot, but if I come into the middle here and I start to scroll out by just taking my wheel and going all the way out, there he is, and that's a lot nicer of a graph. And you can see it goes through the y-axis at x equals 0 and y equals 309. Your exponential functions will always cross at the initial value on the x-axis. So this is a lot nicer than my graphing calculator, but you may not have either one of these available, and you still might need to sketch a graph. And so another option is to generate a bunch of values. If you go into second graph on your calculator, you'll see you have a bunch of values here. 0, 3, 0, 9. That's one of your points. All of these are points on the graph. So you can pick out some of the nicer ones like 7, 329, and maybe keep going to, well, this one's pretty nice, 14, 350.3. And you can pull out points that way. But one of the best ways is to use the idea of doubling. Doubling is going to say how long does it take from my initial value for my amount to double. I started with 309. When do I get to 618? How long does that take? And then you could double that again. From 618, how long does it take to get to 2 times 619, which would be 1238? And that would be a second round of doubling. These numbers are going to be a little bit nicer, and what's pretty interesting is that the doubling time between each doubling cycle doesn't change. From my initial value to the first doubling is the same distance along that x-axis as it is from the first double to the second double. Now, the amount that it goes up is going to be a lot more each time, but once you find out how long it takes to double, you're pretty much good to go. So how do you find out how long it takes to double? Well, here's one way that we could do it. I know my initial value was 309. So I'm going to say 309 here. And then it was 1.009. How long does it take to double this number? Well, 2 times that number is 618. Now what I want to do is I want to solve for t, and it's going to be a little weird at first, but it's always going to follow the same pattern. The first thing that you're going to do is divide by Q naught on both sides, and you're going to see a pattern. So if I divide by 309 here and 309 here, well, anything over itself is 1, and then 618 divided by 309 is 2. That's how we got 618. We said 2 times 309. Now I just have a 1 out front, so I'm going to leave this as 0.1009 raised to the t. And here comes the weird part. You're going to rewrite this using a log. We're going to put this in log form. To change to log form, you're going to start at the base. You're going to go outside to the answer and back around to the exponent. And it's going to look like this. Log base 1009 will give me a 2 when I raise it to whatever this exponent is. Well, that looks pretty strange, right? We're going to have to put it in our calculator a little bit of a weird way. The last thing we're going to have to do is use something called change of base. So we're going to finally change this up a little bit and say, well, I want to write it as log of 2 over log of 1.009. And if I can figure out what that is, I'll know how long it takes to double. So I'm going to need my calculator for this. Let me pause this and pull up the calculator. And on the main screen, I'm going to hit second mode to go back out to the main screen. You see this log button right there? That's what we want. I'm going to hit log and then hit a 2, close my parentheses, and then say divide by another log of 1.009. And then I'm going to divide those two numbers and I get 77.4. It's going to take about 77.5 years for something to double. So if I wanted to sketch this, I can say, well, I know that this is going to be 77 in between here. So 0, this next one would happen at like 77.5. This is going to be about 155, and then that number plus another doubling. And it's easy to find how long something doubles. If I go to 309, of course we know that brings me to 618. The next doubling will bring me up to 1236. And I could plot those 3 points. So that would look something like this, if I can find out how to write. So this would be 77 and 618, about. This would be 77 plus another 77-ish, right? So 154, and that's my 1236. And if I wanted one more, that would be whatever 154 plus 77 is. And then this would be 1236 times the 2, because it's doubled again. So I can get 3 nice points this way. Let's look at another example. I'm going to skip these 2 slides, and let's look at China's coal consumption. So China, between the period of 2000 and 2012, had an average rate of 8% per year that is increasing. If in 2012 it was about 3.8 billion tons of coal, that's a lot of coal, what will happen in the year 2020, assuming that they stay at that same 8% rate? Well, 8% as a decimal, that's going to give me my rate. That's 0.08. That's going to go added into here since it's an increase, and I started at 3.8 billion. So I have 3.8 times 1 plus the 0.08, which of course is just 1.08. And I want to know what happens in 2020. That's 8 years after 2012. So I'll raise that to the 8th power, and I'll get about a 7. If I want to plug this in my calculator, I get 3.8 times the 1 plus 0.08, and then I want to raise this to the 8, and there's about a 7. If I wanted to make a graph of this, we see how poorly it looks on the calculator, and it looks a little bit better on my Desmos, but I might want to go ahead and see if I can figure out how long it's going to take for this to double. So the good news is you don't really have to go through that long process every single time. It's always going to look the same way when you're looking for a doubling formula. It's going to be log, now it says base 10 on our calculator, it just doesn't show the base, but this is a base 10 of 2 over log of whatever your rate of growth is. So I can go through the process of writing out all of that lovely math that I did before, but it's always going to be log of 2 because we're looking for doubling, divided by log of that rate of growth, which is going to be, in this case, 1.08. So I don't have to resolve it every time, right? You can write off to the side, hey, here's my doubling formula, so I can find out how long it takes to double. About 9 years. So every 9 years it's going to double. So after 9 years, in 2021, it will be at 7.6. 9 years after 2021, so 2030, it will be at 15.2. And you can kind of keep going as far as you want to go. Make this a little bit bigger so that you can see the graph. This time for the doubling is always going to stay the same. It's just going to go up by a bigger amount each time. Now the same thing's going to happen if we were looking for a decay rate, but the most popular rate of decay is a half-life. So if I was talking about the half-life of a drug, and I know we talk a lot about medicine in this course, let's say I got an antibiotic that has a half-life in the bloodstream of 12 hours. So that means after 12 hours, half of whatever you have taken has dissolved. So if you take a 10 milligram injection of some antibiotic, one half-life will go by and there's only going to be 5 milligrams left. In this case, this is 12 hours. So if I take my injection at 1 p.m., that's 10 milligrams, that means in 12 hours later at 1 a.m., I'll only have 10. But I want to know what's going on at 9 p.m. That's 8 hours later. Well, my initial value was 10. And my half-life is 12 hours. I'm losing half of it. My decay rate is 0.5. So I would be adding in a negative 0.5 to my rate. So I'm going to put in an 8 up here, which is 2/3. I can go to my handy calculator, 10 times, I can put in a 0.5 or 1/2, either is fine. But up in my exponent, I want to put that in parentheses to make sure that whole fraction stays up in my exponent to get about a 6.3. The half-life, just like the doubling, is always going to be 12 hours. So every 12 hours, you're going to lose half. How much half really is changes, right? The first time I lost half, I got all the way down to 5. But half of 5 is not 5. Half of 5 is 2.5. And 2.5 goes to 1 1/4. This will never get to 0 because you can't take half of something and be left with 0. But it's going to get so close that it really doesn't matter anymore. If you want to find a half-life, you're going to do the same exact thing that you did for the doubling, except instead of having log of 2 up on the top, we're going to have a log of 1/2. So it will look something like this. I have a meteorite. As it decays, the potassium-40 turns into argon. The potassium-40 has a half-life of a pretty long time, 1.25 billion years. You find this rock, and you find that only 8.5% of it is still potassium. So pretend it started out at 100% potassium. How old is this rock if it takes 1.25 billion years for this thing to decay? Well, we're going to need to figure out the age of the rock. If I know this is my half-life, whatever my original amount was, when I divided it by what's left, I get Q. Now, personally, what I do is I just pretend I had 100, it could be pounds, it could be anything. I have 100 of whatever you want to measure that rock in. I know it's decaying at a 1/2. I wonder how long it has to sit there, considering my half-life is huge. To get all the way down to whatever 8.5% of 100 is. Well, that's 8.5. So I'm going to do the same thing I did before. I'm going to divide both sides by the 100. So that gives me 0.085. And I have the 1/2. Now I have it raised to this pretty big T over 1.25 times 10 to the 9. That's not going to be fun. So I need to rewrite this. Remember, start at the base and wrap yourself around. So log base 1/2. I'll get a 0.085 when I get to this crazy exponent. All right, we're going to need the calculator, so let me pause this so I can pull up the calculator. I've typed in our equation so it's a little bit more legible this way. And then what I'm going to need to do is rewrite this now into change of base. So that is going to look like a log of 0.085 divided by log of the 1/2. I'll type a 0.5. It will be equal to the same piece that's over here. So I'll need to figure out what this log stuff says. I'll use my calculator. Log of 0.085 divided by log of 0.5 gives me that crazy number. Now it's this crazy number times all of this. So times 1.25 times 10 to the 9th. So I would need to cross multiply to find t. And I get a super big number. It's about 4.45 billion years old. They rounded. You can see they have the same process here. They came to the 0.085, a little bit of a different way. You can graph the half-life, so once you know the half-life formula, you can just say this is how many years it is and just divide by a half each time if you need to find out what your half-life is or how much is left.